All right, cool. So maybe who has read? I just thought like let's just do chapter 1, right? We're talking about the Haskell book. We're all here to learn some Haskell. I think it's a great language. I've said it a bunch of times. I don't know if it's like the language you're going to replace all other languages with. I don't know if it's that, but it's a cool language to learn because I think it is different and makes you think. Like you start off with a different set of like primitives, and so you solve problems in really quite a different way. And I think that is good because it definitely broadens your thinking in general about programming. And like certainly, yes, it's pure functional. Functional style is a good style. It is certainly a reducer of bugs generally. It's not to say it's the ultimate style. I think you are going to want to use other languages, of course. There's like pros and cons, but like there's absolutely nothing wrong with knowing other ways of programming in other languages, right? So that you can expand the way you approach things. So Haskell's a really good one because it is very pure, it is very functional, but it is also very advanced. So it's taken like a lot of functional concepts and strictly typed and things like that to really not to like an extreme, but to an advanced level. So you can really get into some quite advanced things with Haskell. You can, of course, also, and at the same time, it's also like quite practical. It's actually like really easy to understand at the basics. I think a lot of people just get stuck with like they're trying to build a hello world type of app, and it's like, okay, yeah, hello world is probably one of the more difficult examples of programs to write in a pure functional language. Rather, some kind of mathematical thing is like much easier to do. And those are like really the better kind of hello world examples. So yeah, so like hello world, although it's really easy to write, it's quite difficult to understand. And often things like effects and printing to the console and stuff like that are on the, I would say, slightly more intermediate concepts in a language like Haskell. Anyway, did anyone read chapter 1? So I think the plan for this is to like try to do a chapter at a time. I think that would be quite cool. There's some people joining. We can add them. I don't know how many chapters there are. Oh, there's a ton of chapters. It's like 30 something chapters. So maybe it's not a chapter at a time, but maybe it's like large like sections at a time. Maybe we probably also don't really need to get like super far down in the Haskell book, because I'm sure it becomes, I think once we get through all the like kind of data structure stuff, it's just sort of more zooming. I would love us to get to kind of like the mid-20s or the early early 20s, because I think that's where like all of the value and like all of the very interesting things start to sort of come together. And then after that, it's kind of like a bit more advanced, and then it gets into like basic libraries and stuff like that. And I think we may not even get to Hello World even by the mid-20s. So that's quite interesting. Well, hopefully we can. I don't know. But like the ideal process for me would be to like read the chapter and then like let's discuss it in the session, rather than like I don't want to lecture the chapter. I didn't write this book, and I was planning to kind of like skim through it with you guys now and like see if we can understand it. Does that make sense? Does anyone have any comments on this so far? Have you read any of it? Any comments?
Well, I haven't read the chapter. If I'd known ahead of time that was the plan, I would have totally done that.
Yeah, I kind of didn't have the time to get to it yet.
No, that's fine. Yeah. No, I didn't expect you to, but I just thought like, is that maybe a good idea for like chapter 1 actually is actually got nothing to do with Haskell. It's like the underlying idea, like the computational model we're talking about. So it's actually got nothing to do with Haskell, which is pretty cool. I think actually chapter 2 is where we start with Haskell. Let me just check. I think it is chapter 2. Yeah, hello Haskell. Check it out. So chapter 1 was like is this thing about is a chapter about something called Lambda calculus. But going forward, do we think that's an okay idea? Like trying to read like maybe every 2 weeks we try to like read a chapter. Like I don't think you have to like fully understand it, but at least I've gone through it and go, okay, I get some parts and I've got some questions about other parts or whatever. And then maybe I can try to help like ground that stuff. Does that sound like a good idea?
Yeah, I like that idea. I tried to read the book by myself, and I got up to chapter 2, like somewhere in the middle of chapter 2, and then I stopped. So yeah.
And I watched you
No,
demo
since
your
I-
functional programming thing. So if you got stuck at 2, I might get stuck at the forward.
No, I don't think you'll get stuck at the forward. But yes, okay, cool. Okay, that's cool. So let's do this. We've gone into Hopper's 4. Let's like read through this chapter. So chapter 1. Actually, I think the prelude to this chart was saying is really good. You should read the stuff before this because I think it gives like maybe some of the rationale around why and how and maybe some of the history. I'm not actually 100% sure who the author of this book is, but it is quite a famous book. It often pops up. It's called Haskell book. So often people refer to it as Haskell book. And so apparently it's quite a good one. I haven't personally read it. That's why I wanted to go through it. And I thought it could be cool to do that jointly. Okay, anyway, so let's go through this thing called, so here's a little bit of an intro is, I kind of know what he's going to talk about here. It's about this thing called Lambda calculus. So I'm sure you guys are all aware in your computer science background, you've heard about the Turing machine. Everything we do, like even my Wikipedia is clicked on, Turing machines. So Turing machine, like Turing, Alan Turing, I think is his name, invented like the early computer. I think there's even a movie about this guy, right? Turing. It's quite a good movie. So he invented the like modern computer, and his model was, I don't know it in detail. Probably someone like Maria, you maybe know it in detail, but my understanding is it's like this infinitely long piece of tape, and you have the ability to read from the tape right back to the tape, and you've got like a set of like instructions that execute against the read and write head of the computer. And literally it is that. So like you can build the Turing machine up from like mechanical parts. You can even run it as people. You can as you and your friends can create a Turing machine between you. One of you represents like the tape, and you literally have a piece of paper where you write values on it. Someone else is the computation, and they like read and push and pull values and read and write to the tape, etc., etc. So I think we could probably find like an animation of how a Turing machine works. But like that is the modern computer. It's this idea that you have like effectively you have memory that you can read and write to. You've got like, and then you've got sort of like operations, which are like, I suppose you could think of it as like machine code. You can like read operations off of something, and then you execute them either by reading and writing to the tape, or like moving the tape forward, or rewinding the tape, etc. If that makes sense. And like that totally makes sense, right? So, and from this Turing machine, I think maybe mathematically it is like provable that you can run any algorithm using a Turing machine, right? Let's see what Wikipedia says. So a Turing machine, let me make that bigger, is a mathematical model of computation. Yeah, talk.
Sorry, I posted a link in the chat. It's a video that Veritasium did, but that exact timestamp is when the Turing machine animation starts. It's pretty good.
Oh, cool. Okay. Should I click it? Is my audio coming through?
If you're gonna watch on my side now.
You're gonna watch ads as well. So like the Turing machine exists. Go and click the link, go and understand them, that's fine. But all modern CPUs today are based on the Turing machine. So what is Lambda calculus? Lambda calculus is an alternate mathematical model for computation invented by a different dude. I think his name was something Church, Alonzo Church. Yeah, also at a similar time to Turing, also like the 1930s. And really his mode of computation was not around like reading and writing to this weird tape idea, but it was really just the reduction of mathematical like expressions, reducing expressions down to an end result. And through that, you can also like describe computation. Unfortunately, lambda calculus like didn't win the CPU wars, you know what I mean? Like Alan Turing's machine was the one that was successful, and maybe it was easier to understand, etc., etc. Anyway, like that's what lambda calculus is all around. It's really trying to get down to building a mathematical model for computation. So computation meaning like the ability to run algorithms, or even things like if then else, you know, if else statements, or whilst, or looping. Those are like computations, right? So you can do that with the Turing machine, of course, but you can also do this with lambda calculus. So I think this chapter of this book is just it's starting off with lambda calculus, because it's saying it's good to know it, it's good to understand it, and it, like, you know, it's going down really to like the lowest level primitives in order to, because a language like Haskell is absolutely built on top of lambda calculus. It isn't technically a full-on. I mean, it's not as simple as a lambda calculus. They've taken lambda calculus as its means of execution, but then they've added a whole ton of things on top of it. So let's just like look at this thing. So what is a function? So I think if we think about, I'm just going to make like a new little. You can ignore everything else on the side here. And I even fold that thing away. Yeah, there we go. So like we all know what a mathematical function looks like. We know it looks like, you know, like it could be like f of x equals x plus 1 or something, right? We've kind of seen this before, like a way of describing, I'm not even sure what this is. This is kind of like a line, or yeah, something like that. But this is a mathematical function, right? So I think when they're talking about what is a function, they're talking about kind of a maths type function, this kind of function. So for example, let's imagine a function named f that defines the following relations, where the first value is the input and the second is the output. Okay, the input set is 1, 2, and 3. The output set is a, b, and c. Like we get it, right? So f passing 1 equals a, f passing 2 equals b, f passing 3 equals c, right? Does that make sense? We're not sure what a, b, and c are yet here, but we know that 1, 2, and 3 are like elements, you know. So this would be f of x equals something equals y, and that's the result, right? A, b, and c. So you can imagine that functions are these things that almost translate an element from one set to another set, if that makes sense. Does that kind of make sense to you? If you imagine the world is a whole bunch of sets, so you've got the set of all, so say you have this set, it's like the set of the first 3, what are these, natural numbers other than 0 or something like that? The first 3 natural numbers greater than 0, 1, 2, and 3 in a set. This function f is going to convert from 1, 2, and 3 to the output set of a, b, and c, right? So given this input, I'll give you this output, right? So you can imagine it's like, this is really like mathematical functions, right? And it's really got nothing to do with like computation yet either, I suppose. We'll always return the value a given the input 1, yeah. So that's pretty interesting. So in maths functions, we know this, that every time we execute f with 1, we will always get a. There's nothing else other than a that could ever be the result of this function x. It's like this function here. If I give 3 to that, I will always get 4. There's nothing else it could possibly ever be. So f of 4 always is equal to 5, right? According to this function, there's no other possibility. And so that's almost at the core definition of what is a function. And so here you can see we've like broken the law of function. This is not a valid function. F of 1 equals x, and then sometimes f of 1 equals y. It's like that's definitely not a valid function. Interestingly, like what if x equals y? I don't know, but I'm assuming not. Like these are distinct elements. Okay, given the same input, the output should be predictable. Is the following function valid? F of 1 equals A, f of 2 equals A, f of 3 equals A. What do we think? Does that look like a valid function to you guys? Don't read that. That's the answer there. But it is valid, right? So you can have a function that, given two different inputs, map to the same output. That's okay, right? That doesn't break the law that the same input maps to a different output. Yeah. So like, given one input, it must always map to the same output. This is okay. So 1, 2, and 3 all map to A, and A. So you could imagine the function like, given, I mean, it could be like a Boolean function, like f of 1. This function could be is less than 10. So 1 is less than 10, true. So A being true, 2 is also less than 10 and therefore true. 3 is also less than 10 and therefore true. You know, so that's okay. You can have that, like, obviously that makes sense. So you're kind of like collapsing the input set, something like that. Yeah. Does this kind of make sense to, from a maths perspective, this like view of functions?
Yep.
Anyone not comfortable with this? Good. Marie, are you comfortable with this? Your face just appeared.
Oh, yes, happy.
Vesh, I'm sure is comfortable. Mr. Garvey, you? Yeah? Okay, so you kind of remember this from, I think, standard 8, maybe, hey? Did we learn this in standard 8? Sorry, grade 10? Grade 10?
Even earlier than that. In primary school these days, they learn a little. Do they? Oh, no, it's just variables, not necessarily functions.
Yeah.
I'll tell you when my oldest started learning this.
Yeah.
He's grade 6.
And then at that time, they should learn Haskell as well, because it'll be easier.
Yes.
You won't have to reprogram them from the horrible Turing machine. Yeah. So look, there's our
next step would be being like 14 and being able to do Haskell, like.
Well, actually, like, I do think if you start with this kind of language and you don't know the other kind of programming, this is like actually easier in my opinion. It's like, oh, it like maps to what you do at school. It makes sense. Like, if you should learn maths and Lambda calculus at the same time. They're like, they're the same thing.
Yeah. I would suspect, if you don't have a base to build upon, like, you're building that base with this. So it's not like, if I use myself as an example, I've like got a very like OOP mindset because that's the base that I built.
Yeah.
So going the other way, I need to like kind of rebuild a base to get there.
Yeah, absolutely. But actually, this kind of stuff is just being reminded. Like, you knew this already. You just didn't build your programming experience on top of this. You built it on top of something else. Yeah. So there's our f of x. Check my x plus 1 example is there. Takes 1, which we've named x. The relationship between the input x and the output is described as a function body. I'll add 1 to whatever value x is and return that result. We apply this function to a value such as 1. We substitute. Okay, so this I think is the core of it, is this idea of substitution. We substitute the value for x. And this is starting to show us how computation works. So in this example, let's just put it here. So we start with f of x. I'm going to use their notation. They just use an equals. That's cool. Equals x plus 1, right? So that's the definition. This is like if we define the function to look like that. And now we call it. Let's call it, assuming there's such a thing as calling it. We would go f of 1. And now we know that, like, when we call f of 1, what we're doing is we're substituting 1 for x in the body there, right? So we end up with like, this was the x, that 1 there was what was called x prior, but we've substituted the 1 into there, right? So and then we reduce. So we continue like, well, f of 1 equals, and now it's like, can you guys reduce 1 plus 1 to something smaller? Probably you can. I think it's 2. And like, there's the answer. So it's like, what did we do? So how did we fulfill this computation? Is we just substituted values there. It's almost like there was a line above here where we said, and I'm sure this thing will get into it, but we said like x in the below is going to be equal to 1. So wherever you see x on the left side, like, yeah, wherever you see x on the right side of the equals, substitute 1 for it instead, if that makes sense. And then just continuously reduce as much as you can until you get to like some stable point, which is like you can't further reduce 2, it's already fully reduced. And so that's the answer. So f of 1 equals 2, that is the answer. And so if that f of 1 was in some other context, in fact, you would substitute 2 there as well, if that makes sense. But I'm sure we'll get there. So here we can see the reduction happening. F applied to 1 equals 1 plus 1. That tells us that map the input to the output. 1 added to 1 becomes 2. Got it. Cool. So like, how simple is that, right? Isn't that is like Lambda calculus. It's like, oh, we just substitute wherever we see function names and parameters, we just substitute the body of those functions in there, and we keep doing that until we get to some stable outcome, and that's the outcome. That's the end. That's really how it is. I think though what we probably get, yeah, so I can see this syntax is not quite right because this is kind of mathsy. So what is Lambda calculus? Lambda calculus kind of introduces its own notation. And that's where you see this funny shit starting to appear. So there's this backslash. It's the Lambda symbol. You can often just call it backslash though. And so if we take our funny little definition there, we should have written this not like this, but rather like this. And so that's the Lambda symbol, the backslash. You can imagine that's the Lambda symbol, and then you go dot, and then it's like that's the equals, and then you would go like x plus 1, and that's the body. So that's kind of what Lambda calculus's notation looks like. Start with a backslash. You only ever take one parameter, like all functions take only one parameter. I know you're going to say yes, but surely I can take more than one parameter. The answer is yes, but it's a little bit more complicated than that. And then you have the body. So you have a backslash, your parameter, a dot, and then the body of the function, and you would reduce like that. So I think they're just introducing that. So what does this function do? Does anyone want to take a guess? What does that function do?
Identity.
Yeah, it just returns what they got given.
Yeah, exactly. So, and you would call that the identity function. I don't know if there's such a thing in other languages, but there certainly is in Lambda calculus type languages. You would call this the identity function. So no matter what you give it, it always gives you back what you gave it. So if you pass it a 1, it gives you a 1. So it kind of always maps back to itself. And so that's why you call it the identity function. It is like whatever you give it, it points to itself. So pretty cool. So if you imagine it's sets, it's like the set of all natural numbers. Given any natural number, this function applied to one of those elements will always point back to that original element. It's like very odd, right? But pretty cool. It's a super cool function because you can use it as much as you like. And you can cause no bugs with it because it does absolutely nothing. So yeah, so that's the most basic function, the most basic Lambda calculus function, I suppose. We're talking about a function called f, but the Lambda extraction has no name. Oh, yeah. So that's quite interesting about Lambda calculus is that these functions are kind of unnamed. And you can see that immediately, like when we went from our earlier mathsy definition, at least here we named this thing, we called it f, because we could have also created a g, which takes an x, and it is an x plus 2 or something. And it's like, oh, now we've got an f and a g. With Lambda calculus, actually, we don't ever name functions. Maybe we do. I don't think so, though. I don't think a Lambda calculus has this ability to name things. They're just kind of free anonymous functions, right? So of course that's very useful. I mean, it's very nice. But it's not that practical. So like Haskell allows you to name these things, which is pretty cool. I think it's useful to name your functions, right? Maybe we can name them later. I can't remember. A named function can be called by name by another function, an anonymous function. An anonymous function cannot. Oh, okay, so maybe there's a way to name them. How do we name them? I don't know. Okay, so now it's just defining the bits of it. So it's saying this first part is the head. Okay, so the head is this part, like that's a magical symbol. It's always there, the lambda. Up to the dot is the head. Everything after the dot is called the body. Great. The single parameter of the function. So all functions take single parameters. This binds any variables with the same name in the body of the function. Okay, so they use the word binds. So when you do this x equals 1 thing, you bind the value of 1 to x. So the word bind is a nice word. The dot separates the parameters. Great. Look there, they're saying parameters, but didn't they say there's only one? Wait, what's going on? What's going on? We'll get there. The abstraction as a whole has no name, but the reason for an abstraction is that's a generalization or abstraction of a concrete instance. Okay, so that's quite cool. Oh, yes, they're about to talk about it. Alpha equivalent. So if we look at this function, that one, lambda x plus 1, it is, like, for all intents and purposes identical to this one, isn't it? The function y with y plus 1. In fact, they are the same function. So even though we gave these little parameters different names, they're identical functions. In fact, they are the same function. And so I think that's what alpha equivalence is talking about. Yeah, as long as, and so that's why the like naming of parameters is not meaningful, and the functions themselves have no real names, and so that we can see that they are equivalent. So that's cool. They're saying the following expressions all mean the same thing. Yeah, they all mean the same thing, obviously, right? Happy with that? So no matter which one you reduce, you're going to get exactly the same outcome. Okay, beta reduction. When we apply a function to an argument, we substitute the input expressions for all instances of bound variables within the body of the abstraction. You also eliminate the head of the abstraction since its only purpose is to bind a variable. Okay, that's called beta reduction. Let's use the function we had above. Okay, we'll do our first beta reduction using a number. We apply the function above to 2, substitute 2 for each bound variable in the body of the function, and eliminate the head. It's like, that's a lot of words just to say, like, yeah, we just evaluate. We do this thing, right? So there's just this fancy word called beta reduction, which is to say, if I took a function like this one, let's take this cool y function, and I applied 2 to it, that is saying in the next line, I think I would say here, like, y equals 2, and it's like, okay, well, can we reduce it? So the first step we do in beta reduction is, number 1, eliminate the head, and number 2, substitute the value, the bound value, right? So eliminate the head means kill everything on the left of the dot. So what does this reduce to? So we would take this thing, we would kill the head, which is everything on that side, and then number 2, we substitute the bound value. So, there's a y there, we need to substitute a 2 there, boom, and that's the answer. So the answer is then 3. Yes, you agree with that? So so it's just the process of, it's called beta reduction. Eliminate the head, substitute the bound value, and there you go. Yeah, that makes sense? It's a cool word you can tell your friends. You can beta reduce things, i.e. you can, like, you can execute functions. Yeah. Are you happy with that? Look, this function is the identity function. 10 points for you, Maria. All it does is accept a single argument, return that same argument. Great, good. X plus 1. Here's something interesting. So, like, any ideas what's going on here? I'll make this bigger. Oh, that's better, huh?
Are they applying the lambda function into the identity, so they'll get just back another lambda function?
Yes, exactly. So the same way that earlier we passed a 2 into this function, you could also pass another lambda to the function, right? So the lambda itself, so we could take that example. What exactly is it? It's identity and identity. So it's like x dot x and then they're applying y.y to that function. Oops. So it's like very simple. You could do this without even thinking. You just do, okay, let's beta reduce this thing, right? So we start by looking here at the first line. We say, well, we've got to reduce this thing. So what is it? Like, let's go and grab its parameter. So we know that we're going to eliminate x here, but what is x going to be bound to? X is bound to everything on the right, which is that thing. So x is going to be that, and now we do our things. So we take the old expression, we eliminate the head, goodbye head, and we're left with that, and then we substitute the bound value, which is this. Bonk. Sorry, we eliminate the head and we eliminate the parameter, so we are left with that. Yeah, eliminate the head. I wonder if we should be, I suppose substituting the bound value also means killing the thing that was passed to it, right? So we are left with that. So that, and that is completely reduced, right? We can't reduce that any further. Does that make sense? So that was the parameter. So this was this lambda y.y thing became x, and we substituted x everywhere on the left, and so we were left with y.y because it's the identity. So it's like saying we call the function identity and we passed in identity to it. You know what I mean? And so that returned, like let's write the .NET for this, right? It would be I don't know, some weird return value, identity taking some weird parameter. Or does it go, is it with colons, or I can't remember how C# works. And it's literally going return parameter, right? It's like, okay, and then we ended up calling it with itself. Pretty weird, but that's what happened. It's like a strange example, but it's in the book, so let's do it. So that's how we reduced it. Oh, look, cool. Okay, so they're showing, actually, I've got the notation of this wrong. It normally looks like that. So that's the bind thing. So like lambda calculus is a formal thing, so a formal maths thing. So when you're playing with lambda calculus, it's a good idea to like follow the notation. The notation is like, put the thing you're wanting to beta reduce up there, do on the next line, you're going to put the binding. So you're going to bind x to the thing on the right, and you put this in square brackets with the colon equals, then you reduce it on the next line. And so you can continuously reduce, of course. Here's further reduction. So that's a great one. Let's do that guy. Oh, cool. It pastes the lovely letters, so I don't want those. X.x, and then we've got y.y, and then we had z. So who wants to do this one? Miguel, I'm choosing you. What do we do first?
So I'd assume we start, well, I think we could start either way looking at it, but I would probably say you substitute the y for the z, and then
you want to reduce that way first.
Yeah, just because then that would essentially say, okay, that function evaluates and it returns z. Yeah. And then you substitute that again into the x, and that in turn would return z, wouldn't it? Because it evaluates.
It's left associative. So
okay, so it'd go the other way then.
You were close, but actually it's going to grab the first. So it's going to evaluate this one first. It wants to going to start on the left. So yes, you're thinking, you're trying to pre-reduce it ahead of time. Don't do that. Just evaluate. We're going to evaluate x and the first parameter, which is that. So how do we write this? We go x, right?
Yeah. So it would then be x would be the y and the z parameter together, because that would be one argument, since x is only one argument.
So actually not. No, the z just ends up there. Yeah, we reduce just the first thing. It's just x is going to bind to that. Z is going to hang around. You're going to see.
Okay.
So as we reduce this, I
was going to say, can we not keep the z just outside that square bracket just for visibility? Because it looks like we're just losing. I mean, I know it doesn't say that in the book, but it just feels like we're losing a term.
No, so you'll see as we reduce. Let's go through this step. So what you do is you paste that thing down there. Then we eliminate the head. goodbye head. We eliminate the thing we passed to it, and we substitute x for this thing. Right? So look, z is still there. Z hung around. Does that make sense? Or were you saying you would like the z there? What were you saying?
Yeah, no, so that made it easier for me to follow. But I mean, if it's pretty easy to follow on a small one. I just see maybe if it's slightly more complicated, then suddenly losing a variable just might be a bit confusing. But for now, it's fine.
Yeah, I got you. So maybe some more complex ones, but I don't think so. So let's just follow like the mechanical approach of just saying we cut and paste the top, we put our binding down, we cut and paste the line before. So look, Z has survived because we pasted the whole line, and then we just substitute X in. We substitute X there, and we eliminate the head, and obviously that dies as well. Does that make sense? So Z now remains. And so now there's another reduction we can do here, right? Which is we bind Y to
the Z.
The Z. Good. We paste that down.
I'm starting to see why I normally lose confusion when I've like gone into the more complicated ones. I think I keep starting on the right and trying to go the other way. But I think in this example, it would probably be the same thing, but in more complicated examples, it wouldn't be.
It would, but then you're kind of like you would be passing that whole strange term around. Yeah, absolutely. No, so don't do that. Just so beta reduction actually requires no brain power whatsoever. It is literally a mechanical approach. You could write code that could beta reduce, right? You could, because you just say, well, what is the first term? It's that. It has only one thing ever that's bindable. It's called X. What is the first thing on the right of it? It's that. That's what X is going to bind to. Kill that thing, substitute it in for X, and kill the head. It's like a mechanical process, completely mechanical. There's no thinking involved. It's not like, oh, maybe I want to pre-reduce the thing on the right because maybe the thing on the left wants it reduced first, or there's confusion about that. No, not at all. The left associative nature of it is like, no, just eat it from the left, just eat the terms and beta reduce over and over. So beta reduction is completely mechanical. I think that's kind of the point. I'm not sure if it says that specifically, but that's the idea of it. It is very easy and very simple. So of course you can. Okay, so it does say here, unless specific parentheses suggest otherwise, they associate or group to the left. So we could have, of course, said, if we had bracketed like that, then that would have become the term would have been bound to X. Do you agree? And you're quite right, it would reduce to probably the same thing, I'm pretty sure of it. But if you bracketed it like that, then of course you would have eaten that whole term as X. So it's like whatever is on the right, which is obviously that whole thing. But because we didn't, it just chowed that part. It just grabbed the first thing that it could bind. Yeah. Okay. I think we'll get to more trickies. And point out if I make mistakes here, because I'm like flying I'm on the edge of my seat here. I'm using my memory as much as I can, and I don't know this stuff that well. Onward with the reduction. What is it saying here now? Yeah, okay. So I think we got it right. Eh? Yeah, that looks good. Free variables. Ooh, this is interesting. Yes, free variables. Okay, yeah. Okay, so there's a concept of free variables. You probably have seen this in other programming languages. that you could have functions that speak of things outside of their parameter, right? If that makes sense. Obviously you can, and those things are called free variables. So it could be like we have X, and okay, I see the example goes X, Y, and it's like, yeah, that's fine. You can have. So what it's saying here is like, yes, of course, X is bound as a parameter here. But there is something called Y somewhere, and it's like it's not clear within the scope of this function what Y is, and so it's a free variable. And how do we know? Yes, because it is not named in the head of the function. So while the y is a free variable, the x in the body is a bound variable because it is named in the head of the function. Yes, it is. So the head being the thing before the dot. So we can see x is named. So x is not a free variable, it's a bound one. While y is in the body, but it's not mentioned in the head, so it's a free variable. When we apply this function to an argument, nothing can be done with the y. It remains irreducible. Brilliant. Yes. Quite like, does it make sense? It remains irreducible because if I take this function and I execute it, or I reduce it with 4, we would go like, yes, x equals 4. Great. So we would take that thing up. We would do our reduction and we would say, cool, we can substitute the 4 there. We can kill the head. And it's like, we end up with that, right? For y. And it's like, can you reduce that further? Like, no, we can't, because we don't know anything about y. So that is the result of our function. It remains irreducible. Great. Okay, so you could do that with z. I think we've just done that with 4, so that's good. Oh, look, here they squash this notation inside before the lambda. Maybe that's a nicer way to do it, actually. Since x is the bound variable, all instances of x in the body of the function will be replaced with z. The head will be eliminated and we replace any x in the body with z. Maybe that's a nicer way to do it, other than being on the same line, on separate lines. I don't know. Note that alpha equivalence does not apply to free variables. Yes, okay, good. Yeah. So that's something interesting. I'm not sure how meaningful, how useful this really is for Haskell stuff, but I suppose we're getting through some definition-y stuff. So if you had AY and you had BY, it's like, are these things, I think if they called Y, that could, I don't know. I think it's like those are not alpha equivalent, just because there's a free variable there. They're equivalent up to the A, like they definitely do the same thing on the A and the B. A and B are equivalent, but the Y and the Z are not, and I assume that would be not as well. I'm not sure, actually. I don't know if the story of these free variables, whether they are the same thing.
From what the book says, it should be. So as long as the free variables name the same thing, it should be the equivalent. Because they do, if the minute the variables name something different, it could represent something different.
Something else. Okay, yeah, that does make sense to me. So it means that the free variable called y here is universally the same free variable called y. Yeah, okay. So it does not apply to free variables. That is, x, z, and xy are not equivalent because x and y might be different. However, xy, yx, and abba are equivalent due to alpha equivalence. Yes, okay. Because, okay, so look here. Hey, they've introduced like multiple bindings here. Naughty. xy, yx, abba. Oh, these are not, there's no free variables in these. Equivalent due to that, as are x. Okay, it's more this one. So this is naughty. They haven't told us about multiple arguments yet, and yet they've shown us an example of it. Look, I can see here, multiple arguments. We haven't talked about this. Anyway.
Just a teaser.
Yeah, it's a teaser, exactly. It's a little stumbling block. But yeah, I think this is what we just talked about. X.xz, z is a free variable in this context, and y.yz, it's the same z, assuming the same context, because the free variable is left alone. And so they are alpha equivalent. Okay, awesome, good. Multiple arguments. Okay, so this is actually shorthand. This ability to have more than one parameter. So remember we said earlier, all functions must have one parameter. So how would you create a function that has more than one parameter? It's very easy. So you would say, well, I've got a function. So if I'm limited to one argument, and not 0 or 1, I mean 1, and I want to take another argument, then what I could do is I could just return a function which takes another argument, right? And then I could go like x plus y or something like that, right? That would be one way of doing it. So I have a function which, when you execute it with one argument, will return a function which requires one more argument, and when I give it, it will give me the x plus the y, right? Yeah, so that's like the add function or something. And it's like, yes, that is what you have to do, but there is shorthand for this, and you can just go x, y, and x plus y. But know that under the hood, this desugars to that. There, you know, that this is just shorthand. The second one is shorthand for the first one. We can't break the rule that functions have only one argument, if that makes sense. Yeah. But you can do this in any programming language you like. You can enforce this. This, as I'm sure everyone knows, is called what? Who would like to give this thing a name? I'm sure I'm sure they name it in this chapter.
Currying.
Very good. So good, yeah. And so once again, it's just a mechanical process. So if you see a function like this, you can mechanically turn this line 35 into this line, and it's a mechanical process of going from that to that, right? And then we know how to beta reduce that, so we can mechanically beta reduce that afterwards. Yeah, you agree? So currying, interestingly, is a completely mechanical thing. Once again, it's a pure mechanical approach to functions with more than one argument. Yeah, I'm sure it says here is a convenient shorthand for two nested lambdas. So it's like weird to think of it like that, but actually it's not that weird over time. Think of functions taking one argument. You'll even see this. So in Haskell, it's just a bit of a teaser. You could have a function which takes, say it was the add function. You will see lambda calculus already at the type level, because you will see this. You will see the add function takes an int and an int and gives you an int. And it's like, this is interesting. Like that, it's strange that it's written like this. You might see this in another language, like int add int a, int b or something, and it goes return a plus b. Does that make sense? And so you would say, oh, okay, but this function takes two arguments. In Haskell, you would still write that very much like this. You would say, actually, it takes one argument, and what it gives you is, so you kind of bracket off to the right, remembering that we do that. So it takes one argument, and it returns this thing, which is a function which takes one argument and returns an int. Does that make sense? So you can kind of, like, you drop the brackets, but you can imagine there are brackets here, and then it all makes sense again, and you're like, this is lambda calculus. This is the same. It has the same idea under the surface. So there you can see a little bit of the history shining through. First, a simple example of the identity functions. What are we doing now? Are we going back to the start of this stuff? That looks kind of simple. We did that right. Multiple argument lambda. Okay. XY. Okay, yeah. So I think the point is maybe we should do one of these just to reduce it to see how it looks. And you guys can help me here. So let's go, if we go x dot y and we're saying y, x plus y, and we give it 1 and 2, who wants to help me reduce this? I see Bhavesh. So Bhavesh, you're reducing this one.
Right, so if we're doing left associativity, it's probably going to be...
So do you want to maybe refactor this because it's confusing in this curried notation?
Yeah, I wanted to do it and
rewrite it
in the one parameter thing.
Okay, so it. Let's write it. How does it look?
So lambda x dot, I think you have it on line 37 already. So
yes, you naughty. So it would be, no, but tell it to me. So it would be x, and then the body of this would be a lambda.
Yeah, another lambda, xy, and then dot, and then x plus y.
X plus y. Great. Okay, good. And we keep our parameters there. Okay, so now we can reduce. Let's try. So we're gonna, what are we reducing? What are we binding first?
We're binding x first, I think.
Okay, so and what are we binding it to?
The first parameter, so 1.
1. Okay, good. So I can even do this because I'm a mechanical robot. So I can kill the 1 over there, and I can kill the body, the head there, and I put 1 wherever X was.
Yes.
Okay.
Now we can use Y. So when we substitute
so we bind Y to
Y is now 2.
Cool. And I will robotically do this for you because I'm a robot. I kill the thingy there, I can kill that thing, and now I substitute 2 there.
And then
now
use that to 1 plus 2 is 3.
Yes, isn't that awesome, right? So it's like it seems to hold quite nicely. Hopefully you got that right. Do we make any errors? Shout if you guys see bugs. 1 space 2. What's going on here?
I think they're
doing X. They're not going plus, sorry. Like I'm confusing this with the plus. Yeah. We should remove that. And it's like 1, 2 applied to 1. Anyway, whatever. Exactly. Perfect. So it was reduced to 1 space 2, and that's because we started with X plus Y, not X applied to Y or XY. And like that, that's confusing to me, man. Like, why did they have that in the example? X and Y next to each other. You know.
Could have been
anyway.
Just Y, but I don't know.
Yeah, exactly. Anyway, this is a bit of a problem in the Haskell community, because everyone wants to be very mathsy. But we're not going to be. We're going to be practical. So what does it do next? Let's try something. Yeah, we can't meaningfully apply 1 to 2. Yeah, great. What a good example. Let's try something different. X, Y, fine. And then, do we want to try this one? Anyone want to attempt this guy? Who hasn't said something? Jordan, you can do this one.
I had a feeling that you would be called there.
Only because your name appeared first on my list. I've rewritten it like that, I hope. Yeah. Okay. What are we doing here?
Cool. So I think the first thing we probably need to do is break down the left side. Yeah.
Okay.
So that would become.
Yeah. You want to decurry it first, or are you happy to?
Yeah, I think decurrying it first is probably best.
Yeah, I agree. I think we should. So how does it look decurried? Uncurried.
It would be lambda x.
Yeah.
Dots, and then the body will be another lambda.
Okay.
Lambda y, and then that body will be, I think, x times y.
Well, in this weird example, it's going to be just xy. There's no.
Okay.
Yeah. And maybe you call that times, but I don't think so. In this, I don't think in lambda calculus this implies, like in maths, that it's a multiplication. This is this is actually y applied to x, is what I would say there. But yeah, you're quite right.
Operation. Okay.
Yeah. It's like a no op, exactly. There's no operation there. And you'll see why, because, well, let's see if it makes sense to us later on. Okay, so we've decurried that. Do we want to bind now?
Yeah, so we'll bind the second lambda, which is that z of a to x.
Okay, yeah, so x equals that, right?
Yeah, that guy.
Okay, good work. And then I will be a robot. Check me if I'm wrong, so I can kill that thing. I can kill the head of x there. And I can substitute that for x, right? Did I do that well?
I think so, yes. That looks right.
Okay.
And then the last thing we need to do is we would need to bind 1 to y.
Okay, so we take y, bind to 1. Let me see if my robot works still. Kill the head. Kill that part. Put a 1 there.
Yeah, and then we would just have to do that one more time, I think. Actually, yes, we would, but the second argument doesn't. Sorry, that first one doesn't actually use z.
Yeah, but it doesn't matter. So we still do it, right? We still bind something to z.
Would we bind?
Yeah, let's do it. So it's bound to 1, right?
Yeah.
And then we kill the head. kill this thing, and wherever we see Z, we
it
must
will
put a
just be
1.
A. Okay, so it'll just
And
be,
it's like, oh,
like
it just
one
wasn't a
sentence.
Z, right? So it's
I see,
A,
okay.
I think. Did we get it right? I don't know. Oh, it doesn't give us the answers. Let's try something different.
Oh,
I
if you
think the
scroll a
answer.
little bit, the answer is A.
Oh, good.
Yeah, it's on the
Okay.
next page.
So 0.9
Okay, excellent.
is the answer. Yeah.
Okay, don't look at the answers. I'm choosing the next person, Ruben. We're doing this one.
Borderline anxiety.
Excellent.
Okay, cool.
Yeah, that's cool, man. Excellent. But A and 1. Did I do that right? I think so. I'm just trying to rewrite it from their funny symbols. I think I got it right. Yeah. Okay. What do we do?
Okay, so I forgot the name. It starts with a C. Sorry.
The currying thing. You want to uncurry? Is
Yeah,
there anything to uncurry here, though? So I'm looking at this. So we always look at the first sort of term on the left, and it looks like it is already good, right? It only has
cool,
one
100%.
parameter, yeah. So I think we can go. Yeah.
So it's essentially, we want to assign x to lambda y x y.
This one.
Oh no, it's a lambda z a. Sorry, yeah.
That one. Yes.
Yes.
Perfect.
Okay,
Exactly.
100%.
Yeah, that's the first. Yes, perfect. Okay, and I'll reduce for you.
It's quite unorthodox.
Yeah, totally. No, it's very weird. So I kill the head and I kill the thing I'm substituting, and wherever I see X, I substitute that. Okay.
Yeah.
What do we do?
So I'm thinking that we would say y would equal to. Sorry,
Yeah.
no. Yeah, I'm thinking that we would say y would equal to. So I'm just thinking about that ZA. So y would equal probably to 1, right?
Yes, good. Yes,
Okay, cool,
exactly.
100%.
So that's the lambda, and that's the argument, right?
Okay, yeah,
Perfect.
100%.
Okay, good work.
From
Good
here,
work.
it starts to get blurry for me. That's where I start to lose a bit of
Well, I don't
focus.
think
Now
so.
It's just
So
a mechanical thing happening.
let's just do the mechanics. So we kill that. We kill. Oh, sorry. What did I do? Oh, yes. I must kill the 1. Sorry. Yeah. Kill the 1 and kill the head. And then wherever I see a Y, I should put a 1, right?
Okay.
Okay.
And you're then essentially, then we do the
Binding.
It's just the binding.
So what are we binding?
Okay, also we're basically binding it to 1, is not? Or
Binding what to 1?
we're binding A to 1.
Or Z, right? The first, the head.
Yeah. Okay, the head. Yeah, you're right. Sorry.
Yes.
Okay, that makes
Z
sense.
to 1, 100%. Take that thing, mechanical through it, kill that, kill the head. Wherever I see Z, I must put a 1. There is no Z. So it's like it's A again.
Okay, 100%.
Perfect.
Wow.
Well done.
Oh,
Exactly.
that's weird. Thanks.
Hopefully the answer was A again, if anyone wants to check the answers. This is interesting. Let's try something different. So what the hell does this mean now? Is this a question?
Those are the steps of the computation. That started with the 1, and they're just going through the steps. That's why 9 is A.
Okay, it's still A. Yeah, I reduced the stuff that was already reduced. Okay, good. The next example uses only abstract variables. Due to alpha equivalence, you sometimes see expressions in lambda calculus literature such as this, that, and that. Good. The substitution process can become a tangle of X variables that are not the same X because each is bound to a different head. Okay, yeah, so that's confusing as hell, but quite right. And it's like, of course, like if you look at this thing, like the X is kind of scoped to its body, right? It doesn't also apply to X's in other bodies, if that makes sense. Like we know that, right? We actually do understand scoping of variables, I suppose, in programming, right? So what it's trying to say is like that X there is not the same as that X, obviously, right? So in fact, if we reduce this becomes that x there. So even though, there's another function with another x, which goes xy, and that will be substituted for the first x, right? They're not the same x. Yes, we know this. But it can be confusing for sure. So as you're doing substitution in your beta reduction, you must make sure you only are substituting it within the body of the function that you are evaluating. Maybe it's actually worth reducing this one and seeing. I think this will be confusing. Let's try it. Let's go xy, xy, interesting. X, xy, and maybe this is the last one, right? Because I see we are over time. But I'm pretty sure, hopefully after this, you guys have got it. You can understand the rest of this chapter. But let's try reduce this. Who would like to do this? Who is next? Muchidzi. Do you want to have a crack at it?
Me, I'm a bit confused. So I'm just gonna do a follow-up after the session.
Okay. Would anyone else like to take a crack at it? Who hasn't been? Yes, go.
I'll give it a go, just because I don't think this one is actually answered. If it is, the answer is just as confusing as what it looks.
Good. Okay, well let's get to that answer. Yeah, let's try.
So
what is your approach here?
We'd probably just start with the initial substitution of the first variable from the left being x then, and that would be substituted.
Shall we not uncurry?
Because you don't substitute. We could uncurry it too. So the uncurry, if we want to uncurry, okay, yeah, actually just to
I think we
clear
must,
it up.
because
you must uncurry first.
We can't.
Do you have to uncurry first?
Eliminate the head if it's curried. Yeah.
Oh, okay. So
yeah,
if
we must
uncurry it.
So
it would
actually,
then be
beta reduction. Let's put a little step here. Step A.
Pre-step.
Uncurry. Uncurry the term. What would we call it? I don't know. Uncurry.
Expression.
Uncurry stuff. But you don't have to uncurry everything. Just uncurry the first. Like the first term is all you really need to uncurry. So that's the A. So beta reduction takes 3 steps, A, 1, and 2. Okay, so we're going to
uncurry it. In the actual steps.
Yes. Okay, let's uncurry it. How does it look?
Uncurry it would be, well, /x dot and XX brackets.
So you've thrown away the y. We have to.
No. So the y would come at the end, wouldn't it? So it wouldn't, because the y is at the end. So wouldn't it be XX then a bracket saying /y dot y?
You're overthinking it. It's like mechanical.
Oh, okay.
So to take that, to uncurry that thing, what we do is we put a dot there and then we put a backslash. It's like literally like that's what we do, right? So where you see
the answer
X,
might be
Y,
starting to make a bit more sense, but
we put a dot,
still not entirely.
and then we turn the next parameter into a lambda of that thing. So
okay, so you keep the body and you just keep grouping it together, if that makes sense.
Yeah.
Okay.
So actually, this XXY
is in the nested body.
Exactly. It's in the final, the deepest down lambda.
Okay.
Yeah.
I'm starting to realize where my confusion when I normally look at this is coming in.
Yeah. It is confusing.
It's the overthinking to a degree.
Yeah, don't overthink. Just be mechanical. That is don't try to presuppose it.
At that point, what do we do now? All the variables have been broken up into their individual functions. So now we'd probably do the substitution for x so that you can chop off the head.
So we bind x, right?
Yeah. So you'd bind it to the first set of brackets, which is the x dot xy.
Cool. Good work. So then we can pop that guy down, kill that thing, kill the head, kill that bracket, and wherever we see x now. So here it gets confusing because we're introducing x again, but it's kind of safe. We had 2 x's. These are different x's. We're good. But what we didn't do is we didn't replace those x's. You know what I mean?
Yeah, so those stayed out.
That would have been an error.
I would just treat I thought about that as 2 functions with the same argument names. It's still 2 functions.
Yes, exactly. So maybe that would be a better way to declutter this thing. Is yes, you can uncurry, but then maybe also rename variables that have, rename them, give them other names. X, technically that's x Like this could be X, that's fine. This X is maybe a different X. That should be maybe A, and that X should be B or something. You know what I mean? If you wanted to. But the rule really is remember, we took that, we must only reduce it in there.
Yeah, keep it to its
Reduce
scope.
X in there, not in there as well. Yeah. Okay, but let's keep going. So what's next?
So then, yeah, we'd substitute the Y because that's the next head to hit. And we'd bind it to the x.xz.
Yep, exactly.
Function.
Very good. We can pop that down. We can kill the thing at the back there. We can eliminate the head. Goodbye head. And that guy. And wherever we see Y, we can put it there. And
so would we as well replace the inner ones, correct? So we do replace the inner ones in this case.
Well, yeah.
Okay.
Do we?
That's the part I'm not sure, and that's confuses me if I break it down in my head as well. Because do we go into the nested ones, or would we just replace the last one?
No, we do, because they are in the head. So it's
so
everything under
now in the head because they've been replaced before.
Yeah. So we were reducing that, right? So it's all Y's in this thing, but not in there. Yeah.
Okay.
Should we do that again? Let's just do that again. Okay, so we were saying, yes, we know Y is going to be this, right? Okay, cool. I'm just going to put a space there. So we know we're going to replace, we're going to be evaluating this thing, and we're going to substitute Y for everything in here. And it's like, because I should have eliminated the head last, actually, but it's like all Y's which are in the body, which is that Y, and actually that Y, isn't it? And then we can eliminate the head.
Okay, so
that is confusing. I agree.
Just done the last Y, just because I wasn't sure if you would have gone in, but
no, I think it does go in. Yeah.
Then we'd probably start again with the X again, and then say that X is going to be bound to the x.xz.
That one.
The one at the very.
So remember, we're looking at that guy.
Yeah. So the X. Oh, sorry. Yeah, I thought the one at the end was the end one. Yes.
Yeah. This is a proper mindfuck. Yeah. But it is mechanical. It's like it's not always the one at the end, right? It's just the next one.
Yeah, I thought the next one was the one at the end.
Yeah, I did too. It's a bracketing confusion.
I'm going to try pay attention. I like the colorization. I'll try pay attention
I'm going to
it.
Kill that one.
So then
I'm going to pop that in wherever we see X. This is amazing.
You wouldn't do that one, would you? Because you took a head out. You did one.
You popped it into a head.
Oh, did I?
I think that was right, yeah.
Okay, do it again. Sorry. Oh, I hadn't killed the first parameter, sorry. So it's like I pasted it down. That's the one we're killing, right?
Yes. Yeah.
Then we are substituting this one there. No, it is. It was right. Not that one?
Not the head.
That one?
No, yes, obviously not the head. Sorry.
The XZ and the other, there.
Yes.
I feel like this function never ends.
This
rate.
This is getting worse. It's getting worse.
Might not. Yeah, you can absolutely have functions that never end. And so you can see looping can be a thing here. Okay, let's reduce this horrible thing. So what are we doing next?
Because then you
let's look at our brackets
there, and you'd go to X, Z. Yeah, that one.
Yeah, so X is actually equal to that horrible thing. Correct? So now we can kill that horrible one.
So can I maybe, if we had to have started like you mentioned previously, 'cause I'm wondering if that would have made a difference. If we had started like you mentioned previously, instead of keeping all the X's as different bodies, and we had substituted them to make that they were all separate functions, I don't think we would have ended up where we are now.
Oh, do you think so?
Because you wouldn't, that step where we substituted the inner X's
into the inners. Yeah, I wonder if we shouldn't. We probably shouldn't have done that because they
would have called it P. Yeah.
Yeah. Good question. Yeah, I think we probably did do that wrong. Like, I don't think this X gets substituted, nor that one, because this one belongs to the head. It has its own head, right? So we only
the reason I'm,
replace.
like,
We should only
doing that is
replace in
'cause
the body.
looks like it's getting smaller, then it gets bigger, and then like smaller, and then it like bulks up again. It doesn't seem like it.
No, it's just getting worse. If we now
That's okay,
put that
because-
long one into the next one, it's
Yeah,
just
it's going to
getting,
get bigger.
it's exploding.
Yeah, it's going to get bigger. Okay,
So
so
I'm
let's start
curious,
it again.
maybe let's, after we've carried it, if we change so we leave the first expression as an x, y, x, x, y, and then the second expression becomes maybe b, z,
B.Y.
because then we
you
don't
want
have
to rename.
Oh
you
no,
wanna
I don't want to
rename-
say
The X's becomes Y's.
Well,
No,
we
not
have a
Y's,
y
Y's.
as well, so that's what I'm thinking. If we change
that
we leave those ones,
One
and
is
then
good.
the
We'll
second
make that one
expression,
an A.
yeah, AB, because we have a y already.
B. Yeah, that's fine. And
then
this one
X,
can be C
Z, yeah.
and C.
So I don't think we can change that y to a b, because I think that violates alpha equivalence. I think they
Oh,
said.
sorry. Yeah, it
The
has
Y
got
is
is
a
a free
mistake.
variable.
It's
Yeah,
a free variable, yeah.
Oh,
It's the
okay. So
same
we just change the ones that are
everywhere.
bound.
But that Y is not the same as that Y.
Why
Okay.
not?
Because this Y has got this
it's because it
bound.
has a
It's got a
head.
head. Yeah.
The free
Oh,
y
shit.
versus
He
bound
is a
y.
free. So
Oh,
should
The
we?
first y.
Then you
to
can
a Z.
change it.
We could
or no,
rename that
to a
Y.
B. Yes,
Make
make
that
that a
one
Yes.
B.
Okay, that makes sense. Cool.
Excellent.
Okay.
What about this X? We can rename that X, right? So that
Yeah,
can be
so
C.
CC. Yeah. Okay, so let's maybe see if that that allows us to
And we've
get to a
reduced it.
result.
So we're going to say X is equal to that, right?
Yeah.
Yeah.
And then we'd replace the two
Yeah.
x's
Fill
of
that with
the
an equal space. So that X and that X
yes,
gets reduced, and we kill that and that.
and then we would do the binding again for b, and
Yeah.
we would bind it
The
to the other
brackets in there, so
CZ.
that.
Yeah.
Good.
And yeah, see, it like changes immediately from where we were, because now we're only binding one at this point, where previously we bound like
Yes, it's just
3.
that B. Yeah, quite right. Yeah, quite right. We shouldn't have gone inside. We had no ability to replace that X, which had its own head. Yeah, absolutely.
Mhm.
It was a different X.
So then we'd probably start the reduction again at this point and start with the A dot AY, the first one, and substitute it with its equivalent next to it.
Yeah. We go like that, and then we can say, so we just replace that A, correct? Kill the head there. Did I do that right? Yes, I think so. Should we look at it again?
So, yeah, I think so.
So it looks like that, and we go
Yeah.
A, it's
No, you
only
didn't.
that A. Kill that head, kill that thing. Yeah.
And then if we had to do the substitution here, it'd be A is bound to Y,
Yeah,
because it's the next parameter.
that's right.
Mhm.
Kill that Y. And we can then go Y. Oh, interestingly,
Y and
that's
Y
a
prime?
different Y.
Yeah, is that Y the same Y?
Not
as
the
the other?
same Y. I don't think it is the same Y.
I think it is,
Could it be?
because if you go back up, it comes from the same place of. No, wait. Yeah,
It's
it is,
these-
because we've substituted. There's only one y in the original. If you go to the third line,
It's
there's
the
only
same
one
Y because it's the
Yes.
free variable.
It is the same. It's the same free variable. It's just repeated. Yeah.
Okay,
Yeah.
so we've
Okay, so
taken
we-
the free
Y,
variable
Y.
to the free and we've put it with the free variable, if I'm understanding that correctly.
What does Y mean now? How do you reduce that? You can't reduce Y, but Y?
I don't think we can reduce this any further. Is
You
that
can't
it?
reduce a free variable. Yeah, this
No.
is a bit. But what does Y mean? Sort of.
I imagine that's the
Is it-
answer. Can someone
Is it
check?
Y applied to Y? No.
Yes,
but
Y
you-
applied to Y. It is
Can you
Y
apply a
applied.
variable to a variable?
Well, you don't know what it
Conceptually.
is.
Oh, it
Exactly.
could be a function. Yes.
Could be
okay,
anything.
Fine. Yes. Fine.
It's just an unknown. It's irreducible, right? Because we don't
It's
have
irreducible
anything.
indeed.
Yeah. And there's no head to this thing. So, and that's how we know it's irreducible. There's no head.
Oh.
Okay, good.
Did they give
So
us
it's like-
answers?
Super confusing, right? equivalence exercises.
I feel like this maybe helped me understand the reduction, but I'm still confused.
This is just meant to convince you that you can use maths to achieve computation, right?
Yeah. It's like learning those rules, that Boolean algebra rules as well. I mean, at least that they were slightly simpler and you could intuitively understand a lot of it. But eventually, if you do this enough, you're going to start understanding it as well. It's just applying the rules.
Yeah. So there's an interesting use case of this. I often think of this one. It's like, okay, well, given this crap, and actually this is not the best chapter because it hasn't made it very like applied. It's like, okay, yes, so we've learned the mechanics of doing it, and that's good, and you can see it is mechanical. Like given a set of rules, you can just apply this. So that's good. That's what a CPU wants to do. A CPU wants to just execute mechanical laws, right? Just run through very mechanically easy to process things, and that is a computer, right? Just mechanize your way through it. So great. So you can see how Lambda calculus allows you to do that. Yeah, and even us humans were confused, but we eventually got to the final rules as to how it works.